Come on, recording. Okay. Now, as I'm sure you saw through Canvas, that I got test one graded. That is at least for everyone who actually turned it in. I can't really take the time to go over it in class at this time, just because of someone's been approved to get an extension on it. But I do want to make one very broad comment. Okay, I see we have more people here now. That it happens often in classes like this one where I put out a practice test, that what I will see some people do is take things a little too far when it comes to similarity between the practice test and a real test. And what I mean by that is, yes, if a practice test is meant to give you all a indication of what types of problems you can expect to see, but any of those details can be different. So for example, what I would see in certain problems were using a boundary condition from a problem on a practice test for a problem on a real test, even though the problem statement from the real test is clearly different. Go ahead and compare the problems between the two. So it's one frequent source of aggravation I get from when I put on practice tests, that people just go ahead and carry out what's on a practice test, even though there are differences. Please pay attention to the problem statement on the real test, and be very careful about assumptions that you make. Again, the purpose of practice tests is to give you an idea of what types of problems. Doesn't go further than that. Any detail may be different, and you need to as a class, you'll need to pay better attention to detail. That's all I should say. But now, when I graded each test, I put in comments in the Canvas gradebook, so you should be able to view them. So if you want to find out where you lost points, please look at the comments in Canvas. So it should be possible to navigate to them, like for an entry for that grade in the grade book, because that's where I put them. So if you have questions about where points were lost, please let me know. For those of you who are undergrads, you only had to do 6 out of 7 problems. So a couple of you actually worked all 7 problems. So what I did in that case was just take your best 6. So you got a slightly higher score in that case. I mean, everybody did well. I believe everybody got an A or B. But it could have been better still if there weren't as much carelessness about the problem statement. So please keep that in mind for test 2 and for the final. Okay, let's get the notes going. So we're starting a whole new section of the course. We're done with the heat equation, getting into the wave equation, so a hyperbolic PDE. So what we're looking for, problem we're looking at, the application deals with a we're just going to look at a one-dimensional wave equation for simplicity. A problem modeling the behavior of a vibrating string. Oh, whoops. Okay. All right, so suppose we have a vibrating string, and we're looking at one portion of that string. So starting an interval starting at some x, and then going to x plus delta x. So we have a very small width of segment of width delta x. So what Newton's law gives us about the acceleration of the string. So u, the solution u of xt is a displacement of a string from equilibrium. That the acceleration times the density times the width of a segment can be approximated by these terms here. So we have this force due to the tension. If there's an external force, in other words, leading to a non-homogeneous PDE, then we have that term here. And then we also can account for friction force and restoring force. We're not normally going to deal with these terms, but if we're trying to account for all the forces involved as carefully as possible, then these terms would be there. Okay. I want to focus on the force due to the tension. So really it comes from the tension times sine theta 2 minus sine theta 1, where theta 1, theta 2, the angles that the string makes with the x-axis at these two endpoints of the segment. So if one were to draw a picture, there actually is a picture of this in the textbook, but you can use right triangle trigonometry to get basically what amounts to a change in y divided by a change in x, because and that leads to approximating this force using du dx. And this is rather crude approximation, but as delta x goes to 0, this approximation of this force becomes more accurate. Okay. So what you could do is, if we go to this equation and divide both sides by delta x, then we let delta x go to 0, and this is a PDE that pops up. So this is called the Telegraph Equation. That accounts for any external force, friction restoring force, and also the tension force. This first part here, if we neglect everything else, that is the wave equation. But the telegraph equation is used to describe what's called transverse vibration of a string. So vibration in the direction that's perpendicular to the string itself. So like if we have a string laid out on the x-axis, then vertical displacement or transverse vibration is what this telegraph equation models. All right. Now, so for solving initial boundary value problems, we'll use some ideas that we've seen before for heat equation, like separation of variables can be used. But one thing we need to keep in mind is, because we have a second derivative with respect to time, that means you need two initial conditions. So just like in your ODE class, when you solved first order ODEs, you had one initial condition, and then you moved up to second order ODEs, and you had to impose initial conditions on y and y prime. So it's the same idea here. We need initial data for u of x0 like we did for the heat equation, and also du dt at x0. So initial position and initial velocity of a string has to be specified to ensure a unique solution. All right. Now, the ongoing assumption here in this description of the forces is that the rho, the density, is constant. So we have a string of uniform density. If not, that would change the equation somewhat. Instead of alpha squared uxx, it would be alpha squared ux, and then take a derivative of all of that, so the alpha squared included. So if you have a variable coefficient wave equation, then it would change to this. Just like for the, we had the same thing for a heat equation. If you had a variable diffusion coefficient, that would be lumped in the outer differentiation too. That's just a byproduct of how the PDE is derived in both cases. Now, so the way we can interpret the wave equation is that the acceleration of a string is proportional to the tension, and that is described by the concavity because of the second derivative with respect to x. This PDE can be used in other problems, modeling other situations. One is if you have a rod for a one-dimensional problem, it can model longitudinal and torsional vibration. So the coefficient is referred to as Young's modulus. Also, electric current along a wire can be modeled using this kind of PDE, and this leads to what's called the transmission line equations. So you have two wave equations, one for a voltage, one for a current. Wave equations also show up in Maxwell's equations from electrodynamics. So you basically have a three-dimensional vector field that you're solving for, and it satisfies a system of wave equations, one for each component in the x, y, z. So how can we go about solving a wave equation? So like with a heat equation, we can examine the Cauchy problem, where we're solving the wave equation on the entire real line. So here we have our PDE. Here I'm using coefficient c squared, which is what I use generally. On the whole real number lines, there's no boundary conditions. And then here we have our two initial conditions. So u is equal to f, and then du dt is equal to g. And I'm going to derive a formula for the solution in this case. With a heat equation, we also had a solution formula for a Cauchy problem, but it turned out to be a rather nasty one, an integral that would be very difficult to evaluate. We actually have a solution of a somewhat simpler form in this case, and it's called the D'Alembert solution. And I'm actually going to show it two different ways. One is by looking at this Cauchy problem directly, and then same problem on a finite interval. You can actually use separation of variables to arrive at the same solution formula. Okay. So how to solve this problem? We're going to make a change of variables. So I'm going to define two new variables, xc, which I also refer to as squiggly, and eta, to be defined to be x plus and minus ct. So I'm going to describe these derivatives with respect to time and space in terms of these new variables. And the purpose of that is to drastically simplify the PDE. So I need to do a little chain rule, or a lot of chain rule. So du dx by chain rule would be u xc plus u eta x. So each one of these terms is an application of a chain rule. Or really what we have here, this whole expression is the multivariable chain rule. And I'm expressing derivative with respect to x in terms of derivatives with respect to with respect to xc and eta. Now, if I look at these formulas for xc and eta, I can take a derivative with respect to x. So derivative of xc with respect to x would be 1. So ux would be reduced to this because derivative of eta with respect to x is also 1. So these two parts become 1, and we're left with this. So this is how I can express du dx. But it's really uxx that I need, because that's what I have in my PDE. So to get uxx, I can apply this idea again. So derivative with respect to x is derivative with respect to xc plus derivative with respect to eta. So that's what I have here. This is ux with respect to x. So that's ux with respect to xc plus ux with respect to eta. And now I can take my formula for du dx, this formula, and substitute it into both places here. So when I do that, I get, actually, if I make an intermediate step, oops. Okay. All right. So after I make that substitution from up here, then I can work out all these derivatives. So I have u xc xc that goes here, u eta xc, u xc eta, but those are equal. So I have two like terms that I can combine, plus u eta eta, and that goes here. So now I have uxx expressed in terms of derivatives with respect to only xc and eta. Now I want to do the same thing with the udt. So I use the same kind of chain rule expression. And then derivative of xc with respect to t is going to be c. And derivative of eta with respect to t is going to be minus c. So I fill that in there. So then I can use utt. So I can apply the same idea to udt instead of just u. And by working this kind of expression out again, basically I'm just going to take this and substitute it in here. Then here's what I get. Okay. So now what I can do is I can substitute this and this into the original PDE. And keep in mind that the uxx has to be multiplied by c squared. So notice if I take this and multiply by c squared, I have c squared u squiggly squiggly, and here too I have c squared u squiggly squiggly. These are going to cancel. These terms, because this is multiplied by c squared, will also cancel. So a lot of things cancel. And what I end up with is a very simple PDE. U with respect to xc, then eta is equal to 0. That's because of a cancellation of these terms and these terms. And this PDE, you may remember from homework 1. We know how to solve this. We just integrate both sides with respect to xc and then with respect to eta. And what we find is a solution, a general solution, is an arbitrary function of eta plus an arbitrary function of xc. So how do we choose these? We have to make sure that these satisfy the initial conditions. Questions up to this point? Now, how can we solve for these functions so that the initial conditions are satisfied? So what happens is, if I plug in t equals 0 here, then xc is x and eta is also x. So that's what I get here. But so I'm basically plugging in t equals 0 here, I get this. And that has to equal f of x. Similarly, if I take the derivative of this with respect to t, actually, I'm going to do that here so you can see where it's coming from. Okay. All right, so du dt, all right. So what I need is phi prime of eta, and then derivative of eta with respect to t, plus psi prime of xc, derivative of xc with respect to t. Now, I need to look at the formulas for xc and eta to see their derivatives with respect to t. We go back up here. Derivative of xc with respect to t is c. We use this down here. Derivative of eta with respect to t is minus c, that we also use down here. So now I'll apply that. So I have minus c phi prime of eta plus c psi prime of xc. And that's what leads to this down here. Now here, if after differentiating with respect to t, I substitute t equals 0, then eta and xc both become x. That's what we have down here. So really, what we have for this system of equations, this is u of x0 is equal to all that. And here we have ut of x0 is equal to all this. And these must be equal to f and g, respectively. So now I have this system of equations to solve. Now, before actually trying to solve this, I'm going to integrate the second equation with respect to x. So I'm going to have minus c phi plus c psi. Okay. And that is equal to the integral of this. I'm performing indefinite integration. So I'm going to have the integral of x as the upper limit. So this is an antiderivative. So I need to use a different variable on the inside. And then x naught is some unspecified lower limit of integration. And we'll figure out what that is, or we'll deal with that once we put everything together to get our solution formula. So the reason why I'm integrating is now I have two equations in two unknowns, phi and psi. All right, so now if I write out our system here, I need the first equation. Okay. So now I'm going to solve this. Now to solve this, I'm going to write it in matrix vector form. So I need y'all to put on your linear algebra hats here. All right, so here we have a matrix of coefficients from the system, and then we have our vector, if you will, of unknowns. And then our right-hand side, which are functions also. Okay. Now, if I use a formula for the inverse of a 2 times 2 matrix, or 2 by 2 matrix, just in general, and this is one of those good to know things that comes up surprisingly often, even in a nonlinear algebra setting. Okay. All right, so we divide by the determinants. And then in the matrix itself, we swap the diagonal entries and negate the off-diagonal entries. Okay. Okay. So now I need to rearrange all this. Okay. All right, so psi and phi are what I'm solving for. Okay. All right, so it'll be the inverse of this matrix times my right-hand side functions. But what is that inverse? Well, I take the determinant, I get c minus of minus c is 2c. So I get 1 over 2c times all right, so I swap the diagonal entries. Wait, what am I? Oh, typo. Okay. So I have c minus 1, c 1. Okay. Okay. Now, if I take the 1 over 2c and distribute it through here, then that's going to give me 1/2 in the first column. And then I have minus 1 over 2c and 1 over 2c in the second column. All right. So then what's going to happen is, to actually get phi and psi, I'm going to do matrix vector multiplication. 1/2 times f minus 1 over 2c times this integral of g for phi. And then for psi, I get, or we'll go second row, 1/2 times f plus 1 over 2c times this integral. So if I write all that out, that's what I get here. So now I can use this phi and psi with my expressions for eta and xc plugged in. And that's what I have here. So now I have from this f, I have f of x plus ct. From this f, I have x minus ct, both divided by 2. And then what happens here with these integrals, that I could take this integral and change the sign, and also flip the limits. So now I have, from psi, I have integral from, sorry, okay. I'm going to do this a little more carefully. So you can see how everything works out. Okay. So when I fill in all of this, so for phi, okay. And then also for psi, but here I had to fill in x minus ct for these first two terms. And then f of x plus ct for the last two terms. Oh, right, I have to change the order of limits in this case. Okay. All right. So these two terms combine over here. Here I have integral from x minus ct to x naught plus integral from x naught to x plus ct of the exact same integrand. So I can just add these two integrals together and have an integral. So they chain together because they have a common limit. So the upper limit of this one matches the lower limit of this one. So I add and I get the integral from x minus ct to x plus ct, and that's what goes here. And that completes the derivation of D'Alembert's solution. Okay. So questions about what happened here? Okay, so that's one way of seeing what the solution is. I want to show you another way that, while it's for a bounded interval, it can be extended to the whole real number line from a Cauchy problem. But it also shows how separation of variables can be used, since you're familiar with that already, for equation like this that spatially is like the heat equation, but the time component is very different because we have second derivative with respect to time instead of first. So how do we use separation of variables on an equation like this? All right, so here's the initial boundary value problem that we have. So wave equation, two initial conditions, and then I'm going to impose Dirichlet boundary conditions. So u is equal to 0 on the boundary. So like with the heat equation, we assume a solution of this form, a product of a function of x times a function of t. So using separation of variables, like from the very beginning, you end up with the same kind of situation where you have an expression depending on x equals an expression depending on t, therefore both must be a constant. So that part plays out no differently than it does for the heat equation. So here's what we get. We get the same ODE as we do for the heat equation in space. Everything is the same. The ODE for time has a t double prime instead of a t prime. So as we saw from a heat equation, this is the kind of solution we get for the ODE in x. So that part doesn't change. So then the eigenvalue, lambda in this case, turns out to be n pi over L. So that's what gets substituted in here. So the thing is, notice that the ODE for x and t are the same, except for this factor of c squared here. So remember, the general solution of this ODE was a linear combination of cosine lambda x and sine lambda x. Well, here's a similar idea. We have a linear combination of cosine lambda ct and sine lambda ct. So I'm going to write down here lambda n is equal to n pi over L squared. Oh, sorry, it's n pi over L. So I have lambda squared here. All right. So that's the difference. With the heat equation, we had a decaying exponential because we had a first time derivative here. Now we have second derivative, then it's a cosine, and well, it's a cosine sine, just like 1 for x. Just this factor of c here extra. So now these coefficients, an and bn, have to be chosen so as to satisfy two initial conditions. So because we have, in heat equation, we had one set of coefficients for one initial condition. Here we have two sets of coefficients for two initial conditions. So now we can see what our solution is supposed to look like. So all I've done here is I've taken this and multiplied it by xn of x, and we sum for any and going from 1 to infinity. But then what happens by grouping these trig functions together, and then these two together, is I can use what is called a product to sum identity here and here. And that's what, so using the product to sum identity on this part gives me this, and using product to sum identity on this product of sines gives me this. And notice when you do product to sum identity, your arguments to cosine or sine are added and subtracted. And notice we see once again these same expressions as before, x plus ct and x minus ct. So now what I'll do is I need to incorporate the initial conditions now. So if I substitute t equals 0 in here, well, first, if I plug in t equals 0, here I have cosine n pi x over L minus cosine n pi x over L. This part goes away. So u of x0 is f of x. And I plug in t equals 0, then this simplifies greatly and I get this. So the an are just the Fourier sine series coefficients of f of x, my initial condition. Similarly, if I take the derivative of this whole thing with respect to t and then plug in t equals 0, this part will go away and this part will remain. And I set it equal to g of x, and this is what I get. So bn times c times n pi over L, all of that together, those are the Fourier sine coefficients of g of x. So then, so then what I get is, if I compute these coefficients of f and g, then I'm going to have, from this part, I'm going to have f of x plus ct, because notice this is exactly this when you plug in t equals 0. So the only difference is changing x to x plus ct. And then here, same thing again, but changing x to x minus ct. So that's how I get f of x plus ct plus f of x minus ct all over 2. Now, now here I have g. So if I take the integral of g, okay. So the integral of g from this would be equal to okay. So the integral of sine would be minus cosine. So I have bn. And then, if I integrate this sine, I have to divide by n pi over L, which cancels the n pi over L here. So I just end up with cosine actually I just realized I intended to make this an indefinite integral. Okay. Plus c, the constant of integration. But your Cal 2 instructors always require you to put, or else take points off. Okay. Okay, so then, okay. So matching this with this, except it's again, instead of x, you have x plus or minus ct. Then you wind up with this integral that we also saw from deliberate solution. So in this case, we end up with the same solution formula. It's this physical solution of a wave equation on a bounded interval when you require a solution to be 0 at the endpoints. But then if you take that solution and let the domain grow in size to eventually cover a whole real number line, then you end up with the solution of the Cauchy problem. Since we're a problem in a whole real number line, f and g should go to 0 as x goes to infinity anyway. All right. So this solution formula we'll be working with for the remainder of a chapter. So it's not, so if this is one that's easier to work with in terms of the initial data than from a heat equation, because we don't have an impossible integral. And then we'll be able to use this solution formula to get an idea of how the solution is supposed to behave as t increases, because there's a very interesting phenomena can happen, like waves reflecting and things like that. Okay, so questions about any of this, or questions on anything else, like any ongoing homework? Okay, well, now that I've fried everybody's brains, especially those of you who sat through 610 also, I'll stop recording here, and I will see you on Wednesday with more wave equation stuff.